Hello everyone. This module we will study about condensation. Essentially we will be focusing on Nusselt condensation, that is the condensation taking place on a vertical flat plate. So of course once we understand for flat plate we can extend it for circular cylinders and things like that. So for the condensation, why do we study condensation? See, if we just see these slides, so condensers, where all we come across condensers? Where all we come across condensers in power plant. In the power plant, condenser, water is boiled in the boiler and then condensed in the condenser. So you need condensers in the power plant and in oil refineries. Oil refineries. Oil is evaporated in distillation column and then condensed into liquid fuels. Evaporated in distillation column and then condensed to get either gasoline or kerosene and various variants. Next, desalination plant. Desalination plant. You first evaporate, water vapor is produced, you evaporate the seawater, water vapor is produced and by evaporation and then condensed from brine, that is salt water, and then condensed to get pure water, drinkable water or potable water. So condensation, so there are very many applications. I just stated 3 applications. So there are many applications wherein which condensation is very important. Condensation involves the phase change from vapor to liquid. That is, the enthalpy, condensation involves the enthalpy of the phase change to be removed by the coolant. So enthalpy of phase change is very large. Typically for water, HFG is of the order of 2.5 into 10 to the power of 6 joule per kg at atmospheric pressure. So it's very large. That means the associated heat transfer rates will be very large. So the convective process involved in the process of condensation is it's a convective process. The heat transfer is a convective. Heat transfer to phase interface, that is from vapor to liquid, is a convective process, but depends on the surface, whether your surface is regular or irregular. Based on that, bubbles or film or drops are formed. We will understand that little while from now. Next is, there are 2 types of condensation. One is film condensation. Another one is drop-wise condensation. Drop-wise condensation. Film condensation means if I just take a vertical plate, this is the film which is formed. This is the film which is formed. So this plate might be sitting at 80 degrees Celsius. So this is the liquid film, because the wall temperature has to be lower than the temperature, saturation temperature, then only the condensation can take place. So this is film condensation. So the condensate, so in the film condensation, condensate, that is the water which is coming out, wets the surface, if we take the water vapor, and forms a liquid film on the surface. that slides down, causing mass flow rate because of gravity. Now the whole surface is blanketed by a liquid film, that is why it is called film condensation. The whole surface is blanketed, that is as if we have put a blanket on it, blanketed by liquid film. So this liquid film causes the resistance for the heat transfer. Okay, the film thickness causes the resistance for the heat transfer between the liquid wall and the solid surface. So that is the resistance offered, and the heat transfer coefficients are generally very large. How large? Typically, let us say if you take a steam in a condenses on a tube, on a, let's say 2 centimeter OD tube at a wall temperature, let's say at 300 Kelvin, and the film thickness would be of the order of 0.05 mm, and the heat transfer would be coefficient would be 11,700 watts per meter squared Kelvin. You see the number. Natural heat transfer coefficient was just hardly 5 or 10, and the forced convection you are coming across around 1000 or 2000. If it is water, you will reach around 2000. But now you see the number. It's of the order of tens of thousands, that is 11,700. If the condensate rate, if the condensate flow rate is small, then the flow is laminar. But if it is high, if this condensate flow rate increases, then the flow would turn into wavy, and if it is still higher, it would transit into turbulent film. So you can have laminar film, flow as a laminar or wavy or turbulent, and naturally for each case the heat transfer coefficient is going to be different. In today's module, we are going to derive, assuming that the flow is laminar, what is the Nusselt number and what would be the condensate flow rate which would come, because that's what is the engineer is interested only in the condensate flow rate while he is designing the heat exchanger. So, but the next one is, if you just see, so if you drop wise condensation, we will, in the drop wise condensation, you have a plate and the drops are formed, that is, these droplets would be falling. So that is why this is called as drop wise condensation. So if the condensate does not wet the wall, that is, it is either greasy, dirty, or you have put a non-wetting agent on it, if it is dirt or some grease is there, the droplets are formed, blanket is not formed, the droplets are formed, and then these droplets coalesce and condensation take place, and then these droplets start falling, and they start falling down because of by virtue of droplets will fall down because of the virtue of gravity. So this is what is called droplet condensation, and naturally the droplet condensation would create less resistance because it is not a whole blanket, and heat transfer rates, generally heat transfer rate of film condensation is less than by 10 times, or heat transfer rate for the heat transfer rates more than 10 times are associated with the drop wise condensation, approximately 10 times than the film condensation. It's a too coarse to make this statement, but still, just to get the feel, I just want to say that the film condensation is not good one compared to the drop wise condensation, because the heat transfer rates and the dropwise condensation is very large. And the heat transfer coefficients in the dropwise condensation are typically 30,000 watts per meter squared Kelvin. That itself will explain. I had just told typically H was 11,700 for film wise. For the dropwise, it is 30,000 watt per meter squared Kelvin. So generally we prefer dropwise film condensation. This is preferred. But can I sustain? What do I mean by sustaining? Because to make the droplets, the non-wetting agent has to be continuously be there. So if the non-wetting agent is not there, dropwise condensation will transit into film-wise condensation. So it is very difficult to sustain the dropwise condensation. So generally the condensers are designed on the basis of film condensation. Because even if you design it for dropwise condensation, you are not sure whether you can sustain. So as a conservative estimate, you would settle down for film-wise condensation. So now let us take up. Film-wise condensation. So in the film-wise condensation, laminar flow condensation, of course film condensation, I need not have cancelled this. This is laminar flow film condensation on a vertical wall. So let's say this is my vertical plate. Now initially this is cold wall, this is maintained at the temperature. It is exposed to T infinity, which is maintained at saturation temperature. Okay. Now initially it may be laminar because the flow rates are less. This is laminar, but it may transit if the flow rates increase to wavy, and subsequently it becomes turbulent. So this is turbulent. This is turbulent. So if I were to plot, actually I am going to take little, if I were to plot the velocity, vertical velocity v in the downward direction, this is the x and this is the y. Actually interestingly I am going to choose, this is my x and this is my positive y I am going to choose, okay, because that becomes little easy to derive. So I choose that way. So if I choose that, so you have till the film in the liquid, you have the velocity increasing, this is the interface, this is liquid, and your vapor velocity might be very high. Your vapor velocity will increase and then come to 0. This is my vapor velocity. So that means you will have interfacial shear stress, because there is liquid moving and the vapor moving, there is a shear stress across the vapor and the liquid, that is the interfacial shear stress. But taking interfacial shear stress in the first go, it will be difficult. We will be, while deriving, we will be neglecting this interfacial shear stress, that is del V by del X equal to 0 is what, if we neglect interfacial shear stress, del V by del X term we will be neglecting. So that this is velocity, and if you take the temperature, so this is T wall and this is T sat, and T sat and T infinity might be different, but let me take T sat and this will increase and then there will be a decrease. These slopes are different, and this is delta. This location is, let's say, delta, that is the liquid thickness, liquid film thickness is delta. So this is liquid and this is vapor. So the temperature at the liquid and the vapor interface is my Tsat, okay, and vapor in the descending jet is colder than the vapor reservoir and warmer than the liquid in the film attached to the wall, okay. So that is the temperature is increasing. So this is what we understand, but this problem per se solving would be difficult. So I would limit myself to laminar, and interfacial shear stress we will consider as 0, and I will take a linear velocity profile assuming that Tsat equal to T infinity, and let me state all those assumptions, and let us take only laminar flow. So if we take laminar flow, I am taking, the first thing is Tsat equal to Tsat at constant pressure, and the wall is, this is the vertical wall is exposed to this vapor, wall is exposed to a saturated vapor at pressure P, and the wall is flat. I am taking a flat wall, that is, and the wall temperature is maintained lower than the Tsat. If I don't do this, condensation cannot happen. This is the essential condition for the condensation to happen. This implies condensation occurs, and a thin film is formed, and I am assuming that the film is going to yield laminar flow. I am only considering laminar flow case, that is only the above this, okay. Of course, for this again I will have to redraw. So that is, I take the flat plate, this is my film, this is my Tsat, and this is my X, and this is my Y, and velocity if I take this is the velocity profile, that is it. I take, this is V, I consider del V by del X 0, although it is there, I consider that 0 shear, 0 interfacial shear stress. That it means del V by del X equal to 0, and if I take temperature versus X, if I plot within across this thickness, actually it will be something like this, there will be a curvature, but I would assume that it is linear. This is T wall and this is Tsat, which is equal to T infinity. This curvature comes with the effect of subcooling, so that we will correct later on. Because of subcooling, I am taking saturated vapor. If my conditions are subcooled, then this would be curvature will be there. So with these conditions, and the further assumptions are, because before deriving we should be clear about our assumptions. Laminar flow, constant properties, I am taking constant properties for the liquid film, that is viscosity and densities, and we have taken it as pure vapor. If condensates are there, then there will be complications. We are taking pure, and shear stress is 0. I have taken del V by del X as 0, and I have taken linear temperature gradient. Now with this I am ready to write steady state. Of course, I will consider steady state. Properties are constant means it is incompressible flow. Incompressible flow. So my X momentum equation would be rho L. L means density of the liquid. U del U by del X plus V del U by del Y is equal to minus del P by del X plus mu L into del squared U by del X squared plus del squared U by del Y squared. and rho L into U into del U del V by del X plus V del V by del Y equal to minus del P by del Y plus mu L into del squared V by del X squared plus del squared V by del Y squared plus rho Lg. Notice I have taken plus because I have taken y positive. I have considered y as positive downwards. Okay. So plus rho Lg. Now dp by dy. Now before we get dp by dy, without much complications, let's make life easy. We will say that u is very much less than v directly. U is very much less than v and x is of the scale of delta, which is the film thickness, and which is a function of y actually. Remember that. And y is of the order of length of the plate or the height of the plate, which I have taken as L. So because of this, I can neglect, because u is very much less than v, I can neglect x momentum equation. So what will I get? I get y momentum equation, that is rho L u del v by del x plus v del v by del y, and here del p by del y can be replaced by rho v into g. Notice v, this is hydrostatic pressure. This is the outside pressure which is impressing on my film, like my boundary layer. So notice I am not writing minus again because my y is downwards positive, rho v into g. So you get minus rho v. So that is, you get minus dou p by dou y. So this becomes minus rho v into g. Sorry. So this is minus rho v into g. So you get rho L into g is already there. So you get rho L minus rho v into g plus. Now you see the scale of x is delta, the scale of y is L. So this term can be neglected because delta is less than L. So you can write this as mu L del squared v by del x squared. So this is my y momentum equation. You can call it as boundary layer equation. So what is this term representing? This term represents inertia. And what is this term representing? This is sinking effect. Because of that sinking only, no, it falls down. This is sinking effect. And what is this term representing? Friction. That is because of viscosity. So it is an interplay between inertia, sinking and friction. We are going to make a bold assumption now, otherwise we can't solve this with a closed form solution. Velocities are very less, so I will say that inertia is not so dominant compared to my sinking. Sinking, because of sinking only, all this is, because of the condensation there is sinking. So I am neglecting inertia. So if I neglect that, sinking effect is balanced by the friction. So you get mu L d squared or del squared v by del x squared plus rho L minus rho v into g is equal to 0. Rho L is density of the liquid, rho v is the density of the vapor, just for reminding. What are the boundary conditions? At x equal to 0, v equal to 0, and at x equal to delta, that's what I said, right? Interfacial shear stress is 0. That is, at this delta, I am assuming that my vapor is still and there is no interfacial, and by that time my film velocity also has behaving such a way that there is no interfacial shear stress, that is del V by del X equal to 0. So let me integrate this. Mu L del V by del X plus rho L minus rho V into G equal to C1. Again integration, mu L V plus rho L minus rho V into G. Here it is X. This becomes X squared by 2 equal to C1X plus C2. Now at X equal to 0, V equal to 0. At X equal to 0, V equal to 0 implies that C2 equal to 0. Now at X equal to delta, that is from this equation, del V by del X equal to 0, that is rho L minus rho V into G into delta equal to C1. So if I substitute these two, C1 and C2 in my equation, so I get mu L V plus rho L minus rho V into G X squared by 2 equal to rho L minus rho V into G into delta into X. So V equal to G into rho L minus rho V upon mu L into delta X minus X squared by 2. So now if I take G into rho L minus rho V upon mu L, if I take out delta squared as common, I get X by delta minus half of X by delta squared, that is my V. I cannot be very happy about this equation. Why? Because on the right hand side delta is still an unknown and it is a function of Y. So in the next module, let us derive the delta, Nusselt number and the heat transfer coefficient. So for this module, we will stop here. Thank you.